Shall we? Okay. I think I'm quite audible. Everything should be fine. Hello, and welcome to the stream. I'm Axiom, and this is the introduction of From Papers to Code. It's a new series that I thought of, and it's a series where we'll be looking at interesting articles and research papers from the programming scene, from game development, from research into AI, machine learning, and what you have, right? And trying to implement those in one stream, two streams, whatever, however long it takes. It's a bit for my education as well. I want to be able to keep myself accountable, daily learning, and actually not forgetting how to code, as I do like a side job at the moment. So yeah, that's I guess the series. And for the first episode, I was thinking of making Conway's Game of Life, which is a cellular automata. I've done a bit of research beforehand. I've created my README. So the concept of cellular automaton was coined by the likes of John von Neumann, pretty well known for the von Neumann architecture that is used in PCs and computers, and Stanislaw Ulam, who's known for inventing the Monte Carlo method for approximating stuff, if I remember correctly. And that goes all the way back to the 1940s, right? So it's a pretty old concept. It's been pretty well researched, but one of the most well-known examples of a cellular automaton is Conway's Game of Life. So, what is a cellular automata? A cellular automata consists of cells which live in a regular grid of cells, right? And all of those cells can have a finite amount of states. So, in Conway's Game of Life's version of a cellular automaton, the states consist of being alive or dead, on or off, right? They have two states, which fits the finite state requirement. But that's not all. So you could have more states. And you have a simulation time step, a generation, as it were, which is denoted by T. And each step of the simulation, because this cellular automaton is a simulation of something, you apply a set of rules to each cell, right? You check each grid cell, you check if some rules that you define apply to it. You modify that state if necessary, and if all of the cells get checked, I think my music is a bit loud. When all of the cells are checked, that's the end of one generation, right? So you go over, let's say, this cell, you check if the rules apply to it, you change its state if necessary, then you check this one, then you check that one, and you continue this until you reach the end of your whole grid. And at the end, you have a new state for your, like a new generation. And then you start again, right? This continues, and every time a whole grid gets checked, that's the end of one generation, and you apply the same set of rules again for the next one. And by choosing an interesting set of rules, right? They can be simple, don't have to be very complicated. You can get interesting emergent behavior, right? In our Conway's Game of Life implementation, we have 4 sets of rules, right? And they are as follows. So you have the neighbors of a cell, right? Let's say you check the little cell here. Its neighbors are the 8 tiles or 8 cells that touch it, right? Diagonally or directly on top of and on the bottom. And your aim is, for example, one of the rules is underpopulation. And underpopulation says any alive cell, so if it's alive, with less than 2 neighbors that are also alive, dies. So for the next generation, when we check this cell, we have to change its state from alive to dead. Overpopulation is, again, applies to alive cells. If it has more than 3 neighbors that are also alive, like in this case, it's overcrowded and the cell dies. So for next generation, this cell needs to be survival. If it has 2 or 3 neighbors, right, then it has enough room to, I guess, live for another generation, and it stays on. Now, for dead cells, what you can do is you have reproduction, and that's if a dead cell has exactly 3 neighbors, then it becomes alive. These are 4 rules which result in very interesting emergent behavior, and the goal of this stream is to start implementing this, right? I have created my main file, which is just a hello world in C++. I have my source file. What I'm thinking of doing is, for my setup, I'll set up a build system in CMake, which fetches SDL3. That's going to automatically allow us to use SDL as our windowing and our rendering mechanic. After that, our next step will be creating a grid, which is just going to be a 2D array. We could keep it 1D and try to index it in a way to simulate a 2D array as well. Then we'll render with SDL our grid and the cell states. The next step will be applying the rules to the cells. And lastly, what I'm thinking of doing is slowing it down, because if we were to apply the rules to the cells every frame, the simulation is going to go very, very fast. Right? We could add a delay before updating each time. That's something we could do. But I also would like a button or something like a keybind to press space and go to the next generation that way, right? So we can see step by step what's happening. Okay, so let's first get our build system up and running, be able to get our hello world in here. So not in the source file, here. So CMake lists.txt, right? So we need our minimum version required. I'm gonna say 3.20. Then our project is going to be from paper to code, and we'll use X, C++. So we are going to use C++ 23. Let me check the documentation for this, because I think X standard, I think it was this. And then sets cxx required to on. What else? We are going to include our package fetch content. Fetch content is a optional package in CMake that you can use, which allows you to at build time or at configure time fetch third-party packages and dependencies, right? Instead of vending them yourself, downloading them, and adding them to your project, you can just allow CMake to fetch them from, I guess, GitHub or whatever, from an online place, and then it gets automatically downloaded. So you need an internet connection for this, and then you make it available, and you can then link to it and add its include directories to your project. And then here fetch content declare. We are going to get SDL3. I think it was a repository. I'm gonna have to grab the link. No, it's already. Somewhere. Grab it. There it is. I'm gonna do this. And then, what do we need? A git tag. Which version of the do we need? Oh man, I have an itchy nose. But I am going to mute myself for a second. Hay fever, not fun. Git tag. The latest release is called release-3.4.12. I think, yes. And then git shallow. I'm gonna say true, right? So we don't get everything. This is gonna make it speed up its fetching, and then lastly we need to make it available, right? Fetch content, make available, right? What do we want to make available? Our SDL3 package, right? So just to say like what happened, right? See, I think, yeah. So this is required boilerplate for each CMake project that you have here. You have your minimum required that says okay, this is again opening up on window. Let me restart my explanation. CMake minimum required is saying to be able to use this or like build this package or build this project, you need the minimum CMake of 3.20. It's pretty self-explanatory. You define your project, you give it a name, you say which languages that it uses. This is optional, not really required, but it's interesting information to give to the build system. Then we set two variables, right? Saying the CXX standard, so C++ standard, the version 23, so C++ 23, pretty modern C++. We enforce the fact that it's required, right? Good. We include our optional package from CMake, which is a fetch content package, and we declare which package we want to fetch. In this case, we give it a name, SDL3. This is the link we fetch it from. This is which git tag we want, and we say we want to do a shallow copy. Here we make it available. Now this is good and well. We are getting our SDL, but we still haven't done anything to build our main application, right? So what you do then is you add an executable. Add executable. This is saying to CMake we want to make an executable file of the source files. We give it a name, right? Conway's Game of Life. Conway's Game of Life. This. And we have to give it sources, right? Or source files. And for us that is they are living in source / main.cpp. Okay. Now that's good and well. Our include directories. Doing this, add executable and give it this a name. That creates a target, right? And then we can do stuff to the target, right? We want to say our include directories. Target include directories for which target? Conway's Game of Life. These are private and they are located in SRC. So everything in SRC is available to our target to include. And then target, we want to link libraries. Which library? The SDL library, of course. Conway's Game of Life, again, private. The public and private things, as far as I understand, are there to limit which other targets can see which libraries or directories if they were to include this CMake file, right? If they were to link to this target. That's mostly necessary, I guess, if you are making libraries, right? Static or dynamic libraries. And they have dependencies on some stuff, but a different thing that depend on those libraries don't necessarily have to depend on whatever those libraries are depending on. It's a bit complicated. Maybe we'll do like an extra stream on that. Oh, excuse me. That was my hay fever manifesting. So that was a little tangent. Let's continue. We are linking against the SDL3 library. SDL3. This here, right? The SDL3 : SDL3 is an alias that the SDL3 package defines in their CMake, which makes it easy for us to just link to SDL3. So that's all good and well. Last thing that we need, especially for Windows builds and stuff, is copying over the SDL library itself to wherever the executable lives, right? That is something that is something that happens a lot, where you forget to put the DLL or like the library file next to the executable, which causes an error on Windows saying that some packages are missing, and you can't run your your executable. I need to fix the fact that this keeps doing some weird stuff. Okay. So you can do the copying also via CMake. That's quite neat. But it is quite complicated because it uses generator expressions that CMake allows you to use, and I am not an expert, so I am going to copy this over from here. So we are adding a custom command, right, with a target, right. Our target is Conway's Game of Life, and it's a post build command, right? So this command is going to run after target Conway's Game of Life has been built. Cool. The next thing that we need is, well, the command itself. Command. And then we are saying, second, I need to find here the CMake command, right? Like this. You say -e and then copy if different. Okay. And then what do we copy? Again, some generator expressions. The target file, which is SDL3 : SDL3. Okay. You copy this. Where do we copy it? That's what we define next. To the directory, target file there, of Conway's Game of Life. Conway's Game of Life. Everything correct. Okay. That's awesome. And then lastly, we are going to set another property, right? The target. And that is going to say where to output where do you output the executable, right? Properties, and that is here. Conway's Game of Life. Properties, which is the runtime output directory, and again, that lives in CMake binary there /bin. So what this command says is it sets a property on the target, as the function call says. You give it the target, and the properties you give it are the runtime output directory of this target is supposed to be wherever binary output are, right? The path at the top level of the build tree, so the root, /bin. So the build tree is here, right? It starts at build, and then it's going to create a bin folder, and inside of that is going to live this target output. So this is mostly okay. If everything builds, yes, the builds has been written. To actually build stuff, what you can do is, oh, what's happening here? Let's do this. Okay. Let's see. The CMake build make -b in the build folder. And what do we want to build? The source is just whatever is here, right? If we were to run this, what happens? Okay, builds files have been written correctly. And then the next thing that we have to do is CMake --build. I think that's all that we have to say. now it's building. It's also building like SDL, so that's taking a bit. Okay, so it's been linked. And then what we can do is, if we see in the build file, we have a bin folder and we have the SDL3 DLL and our executable. So our command to run that would be, let's see, build /bin /cgol.exe, and we get hello world as output. So our build has been done. We have made our build system. Let's check if we can include SDL anywhere. Include SDL3 and then just SDLH, right? And if I can say, for example, SDL log, here I can say hello from SDL. Do I need I think this is going to work. If not, we have to initialize SDL. So if I now reconfigure and then I build again, and then I run again, there we have it. So SDL has been included in whatever project we were creating. Now, there's one thing that I want to make life a bit easier, which is in here, a run.bat script, right? Which is just a copy of here. We want to use this, right? I am going to copy this. Excuse me, my hay fever is again. And I am back. So, sorry about that. We will copy this, right? This is to configure. Then, after configuring, what we want to do most of the time is actually building, right? So, we can take this, right? And lastly, again, we are going to run the application most of the time, and that is just following this. And before that, it's always nice to just clear the screen. So if we save this, right, and we go back, we just call run.bat. Everything works immediately, right? Makes life a tad bit easier for us. So the setup is actually done, right? This is our setup. Next thing is, I guess, creating a screen, right? So let me check just how SDL should be initialized for SDL3. I am looking at hello. Yes, that is exactly what I want. That is not 3. So sample. Okay. Here. So in our main, right? We are going to change our main signature to take in an int argc and a character pointer argv to match SDL main that signature. Then we are going to go if SDL init, right? SDL init. Then we want SDL init video. There it is. This is going to give us a boolean, right? If it was able to initialize stuff. Let's just delete whatever we don't need here. Not then we do is return, I guess, this one. Then we are going to create SDL create. There was create window. Create window and render here. So we are going to need a window and a renderer to be able to render stuff to the screen, right? So there's a handy function for that in SDL3. What does it need? It needs a title for the window, a width, a height, and then window flags, and then I guess pointers to pointers of the window and the renderer. So let's first create an SDL window W, right? So this SDL render R. That what's the error? As an incomplete type. Okay, there's a forward declaration in SDL. Okay. Normally everything should be included with SDL3/SDLH, but okay. We'll worry about this later. So title, Conway's game life, right? I guess with let's create some variables for these and width will be I guess 720 by 480 I think it was for 720p and height 480. So and then width and height. Window flags, would that be null? We check. I think 0 is okay. Then window and render. So let's do this, that, right? And what we say is we want the address of W and the address of I think it's going to happen correctly. Excuse me, I had to sneeze. I am going to rename this to window. Rename this to render, right? So do this for a second. And format documents. Okay. Okay. So we have created our window and our renderer. Because this is a game-like application, we are going to need something called a game loop, right? So bool is running. We set that to true. Then we are going to need an SDL event E, right? While is running, we are going to go over all of the while SDL all events with the address of E. While we still have events in our view, we are going to do stuff with them. One thing that we have to do is quit if a quit event has been fired. If we type equals SDL event quit, right? If we have a quit event, then we say is running equals okay, so this will then quit. And before quitting, we have to do some cleanup, right? SDL destroy. Is there like a window and render? Destroy window, which is window, right? And SDL destroy render. What is the render? Now we have to do this in the opposite order, right? We first create the window, then the renderer, and then we have to destroy the renderer and then the window. And then lastly we have to say SDL quit, which is a function. Okay. And if I am correct, which I am not sure I am, this should show up with a the window called Conway's Game of Life. Let's go and open up our terminal and I'll run. Let's see what happens. There you have it, guys. We have a window called Conway's Game of Life. And it does what it has to, right? And if we fire the quit event, it quits. Cool. Another cool thing that we could do is if e.type equals I think, wait, no, that's not how we do it. If e.type equals SDL event key down or up, let's say key up, right? and then if e dots e dots I think it was e dot key. No? Okay, let's try it this way. Is SDL key code key code SDL escape key code interesting. How do you do e stuff? One second. I have to it's a bit rusty. Second. Keyword states, no, that's you type. Key dot scan code, okay. Key dot scan code equals SDL. Okay. Scan code escape. Yeah. Like this, and then it's going to say is running equals also false. This is just a test. Does this work? Sorry, like this. Okay. So normally, if I am correct, pressing escape is going to quit the window. And there you have it. Okay, that's all cool and well. This is fine. It's gonna stay. We could change this later, but this is the game loop, right? This is the poll for the SDL. Anything that we have to do is going to happen here. So this is that. Then we will have a function, I guess, update, which is going to update every frame. And I guess a function draw, right? Or like render. Render is a better function. We can create those. Void update. This normally would need a delta time and timing stuff. For now, it's okay. And then void render, which does not need anything. I'm going to remove this. So we update the state, and then we render whatever we have to. One thing that is quite necessary is the render present. Let's see. This you are going to hear in SDL render present, right? Render. This is going to show the stuff to the screen that you have set up. You have to do this every game. Okay. And then I guess in here what you could do is SDL. Well, maybe this is going to need the renderer, right? Because if you want to do anything, like change the color at which we're rendering and whatever, yeah. And I think before rendering, we have to clear the screen. What does this do? 1 second. Update the screen any rendering performed since the previous call. SDL's rendering functions operate on a back buffer, right? So it does double or triple buffering. And then you have to present it. Okay. One does all drawing intended for the frame, and then calls this function once per frame to present the final drawing to the user. That's exactly what we are doing. You are strongly encouraged to call SDL render clear to initialize the back buffer before starting each new frame's drawing. Exactly, that's what I was searching for. So SDL render clear, right? Again, with the renderer. Anything else that this needs? I guess not. Clear the current rendering target with the drawing color. Okay, so we have to set a drawing color, right? SDL sets render. What was it again? Set render draw color. Color, which is okay, it takes in the render, and then I guess an RGBA color. Let's see, 0x00, and then 0x, I guess 00 again, 0xFF, and 0xFF. So these are hex numbers. So it's going to be completely blue, right? Then we render clear it as blue. We do not do anything in the render at the moment, and then we are going to present. So if I go in here and I say run, we should see a blue screen. There we have it, right? Pressing escape still escapes and closes. This is going to need the renderer as a argument. SDL renderer. So we pass that to it, right? All good and well. And then we could say, for example, SDL render draw line, right? There's a take. Define SDL. Okay, wait. It's just render line. Okay, 1 second. SDL render draw line. Use of undeclared identifier. This is the old name. It has been renamed to SDL render line, not render line F. Okay. and now it's saying it requires 5 arguments. Cool. The renderer, and then x1, y1, x2, y2. Okay. So let's see. We give it this, and then x1 is going to be at 0. Y1 is not 0. Well, we could have it at 0, but let's say height divided by 2. We should probably make those globals, but I don't know. Just for ease of access, having them global would make it easier. And then at 720, and then still at the midpoint of our screen. This. Okay. That's okay. So this should render a line. The issue is it's not going to be visible. We have to set our draw color. Render. No, what was it? Set render draw color. Set render draw color, which again here we can set it to a nice red, I guess. 0xff, 0x00, 0x00 again, and 0xf. The alpha has to be ff. Let's run again. Now we should see a line through the middle of our screen. I'm not sure how visible that is, but there is a line. The issue is it's just 1 pixel. Maybe we could make that a render, not a line, but a rect. Render rect. And this takes in, let's see, frect, yeah. ZL rect R X, Y, W, and H. X and Y again at 0, and then 480 divided by 2.0f. The width is going to be 720, but the height is going to be 15, right? And then I guess we can give it issue here. Yeah, wait. Rect. Okay. It wants an int this time. Sure. And then here we want rect, but I guess it wants the address of. UK effects, and this is not an effect. Okay, that's it. And now this again complains. Okay, so now we are drawing a thicker line, as it were, like this. Whoop. And I haven't closed this. Okay, and we run it again. Okay, so it's not filled, but let's fill it. Now it should be filled and like a red line through the middle of our screen. There you have it. Cool. So this is what we're going to use to create the grid and whatever. Cool. Now, how long have I been streaming? It's been almost an hour. Okay. Let me take a 5 minutes water break, and I will be back. Let's see. In the meantime, I need to make a scene for this. Oh well, let me just mute myself. Okay, I'm back. I think we can continue. So if you go back to the README, right? Let's do this. We have done the setup, right? So we can now draw. We can put stuff on the screen. We have our window. Our build system works. So I think we can go back and this, right? So next thing on the list is we have to create a grid, right? A 2D array. Now a 2D array is pretty easy to create, right? So wait, let's just remove this. Let's see. 2D array. Make some global variables for this, right? Int g. I'm gonna also change these to be globals, right? Rename this to g width. This is not best practice, definitely isn't, but it's just a toy concept. So this now we have our width, our height of our screens. Then what we'll need is I guess the number of columns and rows, right? I'm thinking I just change this to say g height and then g width in here. Static costs. Okay. That's that. I am going to create another rect, right? Frect, rect 2, just to see like a cell, right? How big a cell should be. I'm gonna put this at 50 with a width and height of 15. Now, and then I guess we have to render it, right? We are rendering the cell. Also red, so if I go in my terminal and say run the bat, we should see a cell, like 15 by 15. Yeah, I think 15 by 15 seems fine. Okay, so I go in here, int cell size, you can say it's 15, right? And then we float for rows. The number of rows is going to be the height divided by cell size. One of these has to be float. Let me just set against this. No. Let's make one of these a float. And then I guess float columns is g width divided by cell size. Okay, and then I guess an integer array 2D. We could make it a boolean 2D array. Grid rows and columns. But those can be okay. Just to int, I guess. Not sure how that's going to be. Variable length arrays. I'm gonna have to think about this for a second. So we want rows, right? If we say int, what happens then? It complains because it cannot be narrowed to int. Okay. What if this is also int? Okay, if everything's in int, everything works fine. This has to be a const. Const. It's not a constant expression. Also a const. Let's see if this fixes everything. Okay. Putting const everywhere fixes everything. So we have our 2D grid, right? So if we want to do anything with this, oh, sorry, we're gonna need a couple of things. So the logic, right? We need to have a way to set up the initial state, right? And then we need to go over the grid, right? The rows and the columns. Let's see. I'm just thinking how we should do this. Because I don't want to go into rendering. I want to get the logic right correctly. Let's make a function, right? Void the cell state. This takes in a cell coordinate, right? X and Y. Row. Well, X is the column, if I remember correctly. The row, right? Columns go down. Yeah, they're the horizontal ones. No, they're the vertical ones, and rows are the horizontal ones. Then this does is it goes into the grid at row and column, and sets its state to whatever it wasn't. Right, it flips it. Okay. But then we also have to do some checks, right? If row is bigger, well, let's say first if it is less than 0, right? Or row is bigger or equal, I think, to rows, right? The number of rows that we have, we return. We got log an error, right? And same goes for the columns. The column is like that. With the columns, we know the rows, they go downwards, right? Row, they should be fine. I think. We'll see, we'll see. If not, we'll fix it. That's what we're here for. Okay, I just want a nice way to print, right? So let's see, void grid. For and we want to print. R, right? Zero. R is less than rows. Just press R. And then in here, for int C. C is less than columns, C, and then we want to print, right? How are we going to do this? Let's see out. Grid R T and then need anything? Space, I guess. Maybe. Yeah, not a tab, space. But I'm not sure if it's going to fit even. And then after everything here is printed, I'm going to here, and then it can start a new line. I think. Maybe in here before starting, also see out R, right? R like this. So we print, let's say, the 0th row. It's gonna be 0, and then maybe a tab. A \t, right? Yeah. The thing is, I'm also going to have to do something like if R equals 0, right? If it's like the first row. Where is this? I'm gonna have to loop over like this, right? Well, I want to be able to print the column numbers as well on top, right? So how do you do that, right? You print the row number, yes, sure. But before doing that, right, not even that, it has to happen in here. First, next to each other, you print C, right? C is less than poles, and then plus C, right? And then you're just going to keep printing on the same line. Let's see out. C with a space after. So this is going to print, if I'm not mistaken, from 0 to cols first, right? Then we go in here. This is going to go over each row. Going to go 0, 0. Right? It's going to first print 0. Place a tab. That's going to misalign it, so it should also be a space. And then it prints the column, but that's the column needs to print downwards, no? Hey, let's just try. Let's just try, because I'm going way too deep into yeah, maybe. Okay, this should give me a grid of zeros, no? And grid. I do this, and I go like this, run the bat. Is it going to give me an error? Ah. Okay. Almost. 7. There's somewhere that I'm missing a new line, seems. In here, I guess after this, it needs a new line. Right? Here, new line. Yeah, but also some issues because doesn't exactly line up. Okay, let's try this. Oh, I need to close this. Okay. It says 47, right? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48. Okay, so the numbers are okay, but they are they're offset, which is causing issues. Okay, but proof of concept, it will give you it's a good, I guess, view of what is necessary. Like the single digits are fine, but then with the double digits they start to go off, right? This needs like at least one extra space, right? If it's in the double digits, we could like hard code some stuff, right? Which like the is bigger than 9, right? I guess you just see out an extra space. Would that work? I don't know. We could try. Do this, what happens? Let's close and go back to run the bat. No. Well, I guess kinda. It's bigger than 9. It should do well. 0, 1, 2. You know what? Okay, it's fine. We have some code here that we could reuse in a bit. Let's see if I can flip a couple of cells, right? What if I go in here and I say flip cell states of this is something low, 5 and 5. And I go in here and I say random bat. Is 5, 5 going to be 1? And it is 1. Except okay, wait. This needs to go over these 2 spaces. this. Okay, there it is. Nice, that's a bit better. We fixed it. So, 5 is 1. Okay, that works. Okay. I feel like fixing this. It's fine. It's fine. It's fine. I'm just gonna keep it. This is just for debug purposes. It's gonna stay. But it works. So we can flip bits. We can print the grid. But now we also have to render it, right? So let's just. We have the code to render a cell, right? Let's just set this to cell size. Just so we use our variables, right? Cell size, thank you. So each time we render, we want to be able to render either a white or a red, like a black thing, right? A red cell. So let's see. How do we do this? I'm not gonna render the grid just yet, because if I just render all the cells, that's going to give me a good enough approximation of a grid. Especially if the background is fine, like a defined color. So in here, right? Let's go. We are going to copy some of this code, right? Especially this loop here. So this loops over all the rows, right? And over all the columns. We don't really need to print anything. Here as well. It's just we have to print. We have to check first, like if grid R and C equals true, right? We check that. We then create a cell and we render that, right? Render full rects. Oh yeah, wait. Change this name. Renderer. That. This can go. I am going to take this all the way up. Well, actually, let me put it in here, because this is going to change. Right, so we are going to take that. Where R, no, the X is, it's going to be C times cell size. From into floats, it says. I guess just set the costs to a float. Here. I'm going to copy this over for this, but then with R times cell size. If it's on, right? Let's give it red for now because it contrasts so good. And if it's off, bad. If it's off, then if it's off, we do the same thing with a different color. Well, actually, then you can just take these, right? Do that. If you are going to do it anyway. Like this. If it's off, it is going to be black. But this is just going to paint the whole thing black, right? We need a some play between. So if the X and Y and that, right? Just thinking, is it better to play with its position or with the cell size? Well, I guess with the position, right? What if we do this, right? +1 on both sides. I will see how that affects everything. Currently, there is just one cell that is on, right? So if we do this, yeah, so okay, yeah, everything has been moved by a single pixel, which if we were to like expand this, you'd see the black here overflowing the window. This 5 5, this 0 0. Okay, it's just the grid drawing. It's a bit iffy at the moment. Let's just not do this, right? We'll draw the grids just normally, everything touching. But then at the correct places, we'll just draw a grid overlay. Which is also going to take up a double for loop. Let's see. How do we do this? We are not going to need the ifs analysis, right? I'm thinking single lines. Well, let's use fx to be able to choose how thick stuff should be. So we will set our render draw color not to white, maybe not. 4C. See? That's the color we'll draw our grid lines in, right? Then we will draw up. Let's do it like this. These are going to be two different groups, right? We set the render draw color, right? For the rows, we are going to draw horizontal lines, right? So let's see. We are going to go not over the rows. Well, we could go over the rows, right? We also go over I think just the window height or like width. So grid line is the X is the row height, right? I'm having trouble visualizing this. The rows are going from top to bottom, right? And what changes? The width is from 0 to width, right? So width line here. Width is G width. Height is going to be 2 pixels for now. And then what changes is its X. No, actually the X, it always starts from 0. Right? And the Y is what changes, which is R times cell size. Does that make sense? Yes. And then you do this, right? Grid line. And then you do something similar here, right? Here what changes is this, which is on A times cell size, and this stays at 0. The width is now 2, and the height is G. Okay, there it is. Okay, that's our grid. Okay, cool. And then 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. That's the one that's on. Cool. Okay, we have our grid. We have our internal grid as well. So now, if we go back to the README, we did this, right? We are rendering grid and cell states. Awesome. Now we have to apply the rules to the cells, right? So, that's going to be an interesting one because we have to be able to check the neighbors, right? So print grid is not really necessary anymore because we can see our grid. Let's see. Void apply rules to row and column, right? So we are going to apply some rules. Question is, how do I know if, like, if I'm at 0, 0, right? The top left cell, right? That one doesn't have any neighbors on the top or its left side. I need to be able to say, like, I have to generalize that fact, right? If it doesn't have any neighbors in some direction, I just need to say, like, okay, those are off. Wait, let's see. The thing is, we just need like a neighbor count, right? Like the general for like all cells, and neighbor counts, right? Maybe 0 first. Then what do? We check. Let's think about this, right? Because let's say this is 5, 5, right? Do I have this? This. So I'm just going to go this. Then I can say if this is 5, 5, right? This is 6, 5. This is 4, 5, right? This is 5, 4, This is not. It's 4, 4. And I guess this is 6, 4. And then this is 5, 6, 6, 6, and 4, 6. Right. This is R. This is C. Right. It. Yes, yeah, it is. Well, no, it is CR, no? I have a feeling I'm doing some wacky stuff with these coordinate systems. It seems to work currently, so as long as it works. So this is column 5. The rows are okay. It is C R, right? For any CR, we have to check C minus 1, R minus 1, right? Then we have to check C and R minus 1, and then C plus 1, R minus 1, right? This is that. So C minus 1, C plus 1. That is just this. Here, it is again C minus 1, C and C plus 1, right? So like this. But then always R, right? And then in here it is anything that stays the same. Yes, it's always R plus 1 and C minus C plus 1. Okay. Those are done. Well, you just don't need to check C and R. Well, it depends. You do need to know if it's 5 or that, right? Okay. So. How can we generalize this? With a for loop. I guess, right? So you loop through for int row that starts at R minus 1. And then can only go to plus 1, so R is, while R is smaller than plus 1, right? And plus plus R. Name plus plus. Oh, no, oh, names are getting increasingly complicated. Nope. So that's R, right? Thinking now. Row R minus 1, right? If it's here. And then it's probably going to check downwards first then, right? For int column, which is also C minus 1, right? Column smaller than C plus 1. Cool. Okay. So we do this. It's going to start at R minus 1, right? R minus 1. Going to start at C minus 1 as well. Then it's going to loop until it's equal to C plus 1, right? The C. I think I lost focus somewhere. 1 second. Let's say it's 5, 5, right? We loop over. We start at 4, 4. Because row is R minus 1. And C is C minus 1. Right? Call is C minus 1. So it starts in here, right? The inner loop is going to continue first, right? Okay, it's going to increase this way, right? Until it is T minus 1 is going to be 4, 5, and then is it going to do the 6? Well, while call is 1, C plus 1. Yeah, okay. And then it's going to go, the outer loop is going to increase again. It's going to go in here. Cool. Bool cell states equal grid RD, right? Okay. So if grid row call equal true, right? We plus plus neighbor counts, right? We increase that. So that's how we have it, and then we need an and. Row is not equal to R, and and all is not equal to C. Right, so we don't check ourselves. All right. So this is like a general thing that we're defining. The issue is, what if R minus 1 does not exist? Right? If we're out of bounds. Then we are going to get crashes. We need to fix that in some way. But okay, so we get our neighbor count, right? And then here, if here neighbor count is bigger, what was it again? Okay, if it's less than 2, if neighbor count is less than 2, and null states equals true if we are alive, we flip cell states at our at C R. Not sure why I went with the whole row there, but then else if do I need an else if? An if is going to suffice, I think. Neighbor count is bigger than 3, right? And again, our cell state equals true. This is the overpopulation state, right? Again, we are going to flip cell states at C R. And then for survival, if neighbor count is bigger than 2 and neighbor count is smaller than 3, right? No, if it is equal to 2 or it is equal to 3. I think that was what it was, right? 2 or 3 neighbors, yeah. Okay. So if it is actually bigger or equal than 2 and smaller and equal to 3. Why am I overcomplicating? And again, null states equals true. Then again, well, actually, then we do nothing, right? Cell stays alive. And then lastly, if neighbor count is exactly equal to 3 and cell state equals false, then we say the cell state of C and R to wake up that cell. Cool. Now the issue is we need to check R and C for out of bounds access, right? So row -1. I guess we say if row is less than 0 or row is bigger or equal to rows. We don't return, but I guess I have to do this in the inner loop. What is it? So if you're out of bounds, right? We just continue, I guess, right? Continue, right? Same goes for if column is less than 0 or column is bigger or equal to false, also without increasing the neighbor count, right? Because those are off by default. Does that make sense? So just to test, I am going to see glider. So there is a way to make a glider, right? So that's like a stable pattern which goes diagonally, or like yeah, it travels across the board, it says. Just trying to see how I could do this, right? Just so if I call in the update the apply rules to see something like shooting across the screen, right? I'm gonna add a delay though to the update. So if I go in here and I say, well, to take these, put them here all the way up, apply rules, right? This. Okay. This. Up. And then every frame gets rendered, right? And then I guess I can say as the delay 200 milliseconds. I'm not sure if that's going to be enough, but then I am going to, so if this is 5.5, right? 1, 2, 3, 4, 5. Okay, we need 5, right? 5, 5. That's the Coleman row. This is going to be 5, 4, 5, 3. Right? So 5, 3. And then column 6, 4. Also column 6, and then 5, 5, 5, and then 4, 5. This should be a glider pattern. Glider. Is there something I can copy in here? Just looking at the Wikipedia page of glider. Let's see if everything is going well. No. Interesting. What if I do this? I'm not seeing anything. And there's this delay. And well, oh well. Let's see. Why is that? You apply rules upon every frame for each thing, right? So let's see. SDL main. Think about this. Right. Okay. Events. Yeah, sure. Wait, nothing there. So, what if I put my delay right here, right? SDL delay 200 milliseconds. It's interesting. I am trying to flip these, right? And remove that. Do this, right? They can all be initialized to false. Hmm. I'm thinking. So I know. So a cell with exactly, what was it? Stays alive, right? 2 or 3, right? Oh well, actually, doesn't can be n, right? Be like this. So if I add, wait, 2 neighbors to this, right? Like that. That should be a permanent thing on the screen. And yet it isn't. Okay, where is my shoe? Because if I do not update, right, it's just for a second, and I run this, I should see that, right? That cell, it should stay alive. Okay. We know the renderings is not the issue, it's the fact, like the apply rows seems to be problematic. Wait a second. So flip cell state column 4, row 5, right? Is this correct? Zero, 1, 2, 3, 4. Column 4. Wait, 0, 1, 2, 3, 4. Okay. 0, 1, 2, 3, 4, 5. And then the row is correct. Okay, no, column and row seems to be correct there. So what's the issue? What's the issue? if the neighbor count of a certain cell is less than 2, right? If it has 1 neighbor or 0 neighbors, and the cell is alive, then it becomes dead. Okay. If the neighbor count is bigger than 3, thus not 3, I feel like it's... Oh, wait. Well, no. This is rows, right? No, it's fine. I don't have to go over every pixel. I have to go over every cell, right? Yeah, like calling update, right? It goes in here. It takes in the cell state of the cell that we're correct, like checking at the moment. It says, okay, alive neighbor count, maybe that's a better name. Count. -1. Row plus and R is 1. And then row have to be like this? Not sure. If A and row is not equal. Okay. Okay. No. What is the issue? Let's do this, right? And let's print some stuff. Alive neighbors of this and then this. And then live neighbor count. And just include this for a second. Let's run. Okay, 1 second. And it's all just zeros, right? Scrolling up. Okay. This thing. This. 5, 5, and 4. Right? And then I am going to just update for. Let's see. Update every 5 seconds. Right? Just test this out. I'm going to close this. Oh, come on. So it printed it out twice. Right. Going through the terminal. Okay. And I think that's our issue. Wait. Let's just go back. Should be somewhere here. It says 1, 2, 3, 4 live neighbors. Which is weird. Wait, is there? Okay, no. So 3, 4 has one alive neighbor. Okay. 3, 6 has one alive neighbor. Okay. 5, 5 should have 2 alive neighbors. Normally. But 5, 5 is not being checked. That's the issue, I think. Wait. Yeah, I am skipping. Uh, 5, right? What if, right? Let's try again. Okay. Okay. So we go back. Oh, but this is not going to happen. Bad. Must have been and, right? Okay. Let's just do this. Come on. Okay. So up to the previous thing, right? In the first you call it in the first generation, right? The initial state. 5 should have 2 neighbors. And it does, right? But 5-4 also has 2 neighbors. Does that make sense? Okay. What was it that I did here? So 4-5, 5-5, and 5-4. So wait. 4-5, 5-5, and 5-4. And we see 5-4 has 2 neighbors. Yeah, these 2. Okay. Makes sense. 5-3 has 1 neighbor that's 5-4. Okay. 5-5 has 2 neighbors. Makes sense because 5-4 and 4-5. And 4-5 also has 2 neighbors, right? And 5-6 also has 2 neighbors. 5-6 also has 2 neighbors, yes. Okay. Okay. Let's see, 4, 5, and 4, 6 also. And 4, 4 has 3 neighbors. 4, 4 also. Yeah. But 4, 4 is not alive. So it'll become alive then. Okay. So if I now do this, right? And I just say 1,000 milliseconds instead of 5,000. And we go in here, they run the bats. Let's see what happens. Okay. And it stays alive. Okay. So let's make a glider again, right? Glider was so have 5, 5, and then 4, 5. Let's say also 3, 5, right? Okay, 3, 4, 5. And then 3, 4, 5. This is it's 5, 5. This is 4, 5. This is 3, 5. 5, and then this is then 5, 6. 5. Oh, sorry, this is 5, 4. And then 5, 3, 4, 3. 4, 3. This should be a glider, I think. Not exactly, it seems like. 3, 5, 4, 5, 5, 5. And do I have to flip this? 5, 3, 5, 4. 5 and 3. Okay. Almost. Something was happening. Wait. So I am going to try again. That is 3, 3, right? 4, 3. Right. 3, 4, 3, 5. 4, 4, 4. 3 on the bottom, right? Yes. 3, 4, 3, 4. Four, 4, 5, 4. Okay. Coordinates, man, they're hard. Third row, third column, third row, fourth column. Okay. Okay. Row, fourth row, fifth column. Okay. Fifth row. So it's going to be fifth row, third, fourth, and fifth. 3, 4, and 5. Okay. Oh, that is not what I was searching for. Yeah. Okay. Okay, no, I think I have the glider correct, at least, right? I think there's still like an issue here. These else's might be culprits. Nope. There is something wrong. I don't know. I feel like there's like a small bug. Yeah. What if? I don't know. I feel like my issue lies with the fact that I'm kind of guessing with the rows and columns. I feel like everything should be fine. Well, maybe. Thing is, I am setting 1, 2, 3, 4, 5 cells, right? But I guess my first frame already immediately kills a couple cells, right? Yeah, I think my issue lies right here somewhere. The number of neighbors that are alive to any given cell, less than 2. And that cell that we're currently checking is alive. We flip it, right? It dies, right? Same happens. Under population, was it? Overpopulation. Survival and repro. Yeah, that wasn't it. Oh wait. Should I just add like returns? Because if anything happens, it doesn't need to check it. As well. Here, return. And after doing that. Maybe it's interfering with each other, I thought, but I guess not. My rules you incorrect. Search. So any cell that is alive, right? But has less than 2 alive neighbors, right? It's alive and it has less than 2, then it dies. Any cell that is alive with 2 or 3 alive neighbors, right? It stays alive. You don't do anything with it. Any live cell with more than 3 neighbors dies. It's more than 3. Also dies. Then, if the cell has exactly 3 neighbors and it is dead, right? It's not healthy, true. It becomes alive. So okay. No. Interesting. I am going to take a break. And then we'll do like a last bug fixing session, I guess, to get this working. Because I cannot find my mistake. But yeah, I'll see you guys in a bit. Okay. Um, yeah, so I looked a bit around and I see my issue now. The thing is, what we're doing right here, or what I'm doing, is I am updating this grid in place, right? And as I kind of suspected already, it's affecting the state of the next cells that are being checked, right? Because the grid already has been updated for the previous cell. So what we need is we need to be able to look over the whole grid, right? Without updating it yet, and put the next generation in like a different buffer, right? So something this actually. So the next grid, right? That's the same thing like here. Then here it is the same, right? Cell states, your alive neighbor count, you have to check those. This is looking at all the neighbors, right? This is all correct. And then here, right? So here we want the next state, right? Next cell state. We say it's the same as the cell state first, right? Then comes the rules, right? If we have less than 2, right, that is underpopulation, we flip the cell state. Well, this flips it in the actual grid. That's not what we want. We want to change this to false, right? For the next, it's going to be like that. Overpopulation, same thing here. Also false, right? We don't need these returns. Okay. Survival, that's the same, right? So say like that. But if it's false, right? Then it's going to be next state. It's going to be true in this case, right? And then what do we change is with the flip function that we used to use, that would change the grid, right? The actual grid. What we just need to change is next grid. That's row and column. Is going to be the next cell state. Not equal like this. But after applying the rules, only thing that we need here is mem copy, right? Destination, the grid. The source is the next grid, and the size is size of just the grid, because they're both the same. Next grid could also work. So as far as I can tell, this thing should fix it. And there it is, right? We have our, what do you call this? It had a special name. I don't know. But like if you have just 3 cells next to each other that are alive, then they just flip, right? So let's try and get the glider again. Glider. Here, so column 4, row 3, 4, and 5. So this is like vertical, right? We want that to be changed 3, 4, 5, and these are going to be at, I guess, 3 is fine. So this is like a horizontal on row 3, right? Then I am going to need one at row 4, one up, and one at row 5, but that is in the middle. This should be a glider, right? I am going to bring back a delay. Delay of what? 50 milliseconds, right? And if I do this now, okay, that went the wrong way. I wanted it to go down. Well, row 3. Glider, glider, glider. How do you make one? See, so if I say 3, 3, 3, and then this 3, 4, 5. Okay. 3, 2, 5, 2, 5, and then 1, 4. I think. Yeah. Oh wait, no, you can't see it. Dang it. 1 second. Enable. Try again. There we go. We have Conway's Game of Life. Well, basic implementation. And it works, right? We have a glider. It's not an infinite canvas yet. Maybe that's something we could do, or we could just make it big enough so it seems infinite. But cool. That was 3 hours worth of work with a couple bugs, but we got there in the end. Yeah, so that was fun. That was interesting. And I am getting a message. All right. Well, thank you for watching, and that was the first episode of From Papers to Code. See you in the next one. Yeah.